So, welcome everyone. Let's make a start. We still have a few people entering. So, welcome everyone to the first ever Cook the Science lecture. I'm Thomas Michaels. I'm a professor of soft and living matter physics here at ETH Zurich in the Department of Biology. Next to me is Rebecca Clopath, is our invited guest and chef for tonight. So she's going to do some amazing cooking. But first of all, I would like to say a few words about Cook the Science. What is it? Why are we doing it? So soft matter physics is probably not something that everybody is familiar with. You may ask, what the hell is soft matter physics? Well, soft matter physics is the physics of soft materials. And soft materials are everywhere. You think about in physics typically about hard solids or liquids. However, if you look around you, you probably notice that most materials around us are something in between. They're not quite really solid, they're not just liquids like water, but they are somewhat in between. Like this sponge that I have here, or the mushrooms there, or that beautiful sauce. So these are all examples of soft materials. So it's a really exciting area of physics. It's very relevant for biology, and that's where my research goes. So I'm trying to use ideas from soft matter physics to understand biological materials, which are for the most part soft matter. But what makes soft matter very interesting is that in the kitchen, you have a lot of soft materials. And so cooking is an amazing way to tell you about how exciting soft matter is, because everything we do in the kitchen, from making a sauce, an emulsion, a cake or so, has to do with soft matter physics. And so what I want to do with Cook the Science is to excite you about this fantastic field of research of physics and biology. And we will go through different examples of how soft matter appears in the kitchen. So we'll have a series of lectures. Today is the first one. Each night we have a different topic from soft matter physics. Tonight is heat transfer and browning reactions. And in each event we will have also a chef that will help us to understand and visualize and actually, I guess, maybe eat as well, some of these delicious soft matter creations. And so you can see the list of all the lectures that we have this semester, and we will have more lectures in the next coming semester. And for me, it has been really exciting to see how many people have signed up to the lecture. I mean, there has been a huge success. We ran out of spaces very quickly, as you have noticed. So we were able to get a larger room, which is great. So we could host more of you tonight. So the way it's going to work is we'll have pretty much the same format every night. I will start with the boring part. I'm telling you about the science and the soft matter physics. And there will be equations. And the idea is that you should clap whenever you see an equation. So watch out for the equations. And then after the boring scientific part, then we will go on to the chef show and we will see beautiful recipes. But the idea is that we will try to see how the physics and science concept helps us to understand why we are doing things in the way we do. So why is a recipe working in a particular way? So the topic for tonight, as you can see, is heat transfer, charring, browning, and flavor. And because this is the first Cook the Science lecture, I thought we should somehow start from the basics and ask ourselves, what is cooking? So I guess you find a lot of definitions around, but this definition here is probably not a bad one. Cooking is the process of preparing food by heating it. I guess it's for most of the preparations we do, it's probably correct. I would say it's maybe a narrow definition because you can cook in different ways. You can cook also by pH, by, for example, adding an acid. So that's how you do, for example, ceviche. Also, so it's not only about heating, but in most cases we would say it's probably about applying heating. But why are we heating food? To cook it. So the idea is that whenever we cook, what we want to do is we want to induce some type of transition. And this is the concept that we have in physics of phase transitions. And so I guess probably the students from among you, we're gonna scream now because, phase transitions are not a simple idea. But actually, if you think about it, it's not very hard. So here the idea is that we have a temperature axis and we have some food, for example, egg, here, which at a certain temperature, we would say it's raw, and then we heat up the egg, and at some point we say it's cooked. And what is very interesting is that this process of cooking here happens typically at a particular temperature. So when you cook egg, you know, for example, that you have to reach a particular temperature of about 63 degrees in order to induce a phase transition, effectively going from the raw egg to the cooked egg. And so this is a very similar concept to what we have in physics. And you're probably all familiar with this concept of, what we call a phase diagram, for example, for water. So you all know that water can exist in different phases. It can exist in a gas phase, in a liquid phase, in a solid phase, and this depends on temperature. And so there are characteristic temperatures, 0 degrees from going from the solid to the liquid phase, and 100 degrees from going from the liquid to the gas phase. And at the molecular level, we can understand these transitions because effectively what happens is the molecules are in a kind of ordered, almost crystalline-like fashion in a solid, and then they start to flow as we heat them up, and then they become much more dispersed and they move much faster in a gas state. Now, this is very similar, as I said, to what happens, for example, when you cook egg. When you cook egg, you are also introducing a phase transition. But if you think about it from a physics perspective, it's a kind of unusual transition, because typically you are used to the idea that as you increase temperature, things become, let's say, liquid and then gas. Whereas when you heat up egg, it starts off liquid-like, and then you heat it up, and then it becomes solid. So it's a kind of weird phase transition if you think about it, but it is a phase transition. So what is happening when we are cooking egg and we are increasing the temperature? So what is happening is a branch of things. Among these things is protein denaturation. So proteins denature with temperature, and so you probably know what proteins are, but I think it's good to remind ourselves what we are talking about. So proteins are strings of amino acids. So they are like long chains of these molecules that are called amino acids. They are like an alphabet. And this is what we call the sequence. Now, typically the sequence is not the only thing about proteins, in the sense that proteins, in order to perform their functions, they have to adopt a particular three-dimensional shape, which we call the fold. So this process is called folding. And now what happens is when you cook or when you apply heat, these proteins start off in the folded state. This is effectively what raw egg white is. And then you apply heat, and then the proteins effectively unfold, so they become these long polymer chains, and then they stick to each other and they form aggregated structures, and this gives the solid-like structure to the egg white. And so effectively, when we are going from the raw egg to the cooked egg, what we are doing is we are inducing a set of phase transitions of proteins that start in a folded state and then unfold and aggregate and give rise to this a solid-like structure. Of course, in egg, you have different types of proteins, so the temperature at which this process happens for different proteins is different, and so you can reach different results in terms of, thinking about the yolk, the egg white, and so on. So by playing with these temperatures, you can control effectively the amount to which the egg is cooked. Now, these type of transitions are induced by heating food. So what we want to do is effectively we want to heat up the food to a point that in the inside, for example, the egg yolk here, we reach the target temperature that we want in order to induce this transition and cook, for example, the egg yolk. And so this process of effectively using heat, oh, excellent. Very good, very good, very good. So this is the first equation of the night. Actually, when does it happen that students clap to equations? I mean, that's... So this process is called heat transfer. And it's probably useful to kind of think about what is temperature from a physics perspective. So temperature is effectively the motion of particles. Okay, so the higher the temperature, the more kinetic energies particles have. And this is this equation. M is the mass of the molecules. V is the average velocity of the molecules. Here it says EA, it should say V. KB is the constant, and T is the temperature. So the higher the temperature, the more velocity these particles have. And so what you want to do when cooking by applying heat is you have your food, which for a physicist is always a sphere. So that's always what happens. So let's say, okay, we have this spherical food. You apply a particular temperature from outside, for example, by putting it in boiling water or put it in contact with the pan. And then heat slowly diffuses into the center of the food. Heat always goes from high temperature to low temperature. And at a molecular level, we can understand that actually pretty easily with this picture of the motion of molecules. So when you apply heat from the outside molecules are very excited, so they move a lot. And then they start bumping into the colder molecules. And by bumping into that, they give part of their energy to the slower molecules that then start to move faster. And so this is the way in which heat is effectively transferred. And it takes a little bit of time until this happens, but effectively what you want to do in cooking is you want to cook the food long enough such that the internal temperature reaches the target temperature that you want to induce this phase transition. Okay? And this is what we call is cooked. Now, here is a recipe from Rebecca. She will show us how to do sautéed mushrooms and really nice stuff. But what you can see here is that in order to sauté the mushrooms, you have to put them in hot oil. So you have to cook them at really high temperature. However, the type of phase transitions that I showed you before that you need in order to cook food typically happen at relatively low temperatures, 60, 70, 80 degrees, and typically lower than the boiling point of water, lower than 100 degrees. So what we could do technically is we could just put the mushrooms and put them in boiling water or cook them at 60 degrees and wait until eventually the temperature inside the mushroom reaches the target temperature. That would work. So why is it that we cook the mushrooms at high temperature? Why is it that we want hot oil? So the idea is that what we want to do is we want to induce something else. So we don't just want to cook the food for the sake of cooking it, so induce this physical transformation, but we want also to induce chemical reactions. And in particular, we want to do browning. And browning reactions are an amazing set of reactions that give body and flavor to foods. They are the flavor reactions, if you want. And the two main examples are caramelization and the Maillard reactions. And so we will see examples of these tonight. And so how is it that these reactions give flavor to food? So let's start with caramelization. So caramelization is probably the simpler one in these two examples. And caramelization is effectively what happens when you heat up sugar, literally table sugar. So you take sugar, you heat it up above a temperature about 160, and then you get caramelization. And this is a reaction that generates hundreds of byproducts. It generates brown compounds that give the color brown, and it also generates flavor compounds. And so the way you can understand this is that sucrose, which is like table sugar, effectively it's a molecule like this. It is made of two smaller sugars, glucose and fructose, that are connected. And then when you apply heat, what effectively happens is you break this molecule and you release the glucose and the fructose molecules, and then further reactions happen whereby these molecules further break up into smaller molecules, they rearrange, they form new compounds, and eventually you end up with hundreds of products. most of which have flavor. And here are particular type of examples, like for example, this molecule here has this toasty, caramelly taste. This molecule here gives the nutty, caramelly taste. This molecule here gives, for example, the buttery taste. So you are releasing all of these compounds from the breaking up of these sugars at high temperature. Now, this is the second reaction, browning reaction, is the Maillard reaction. This is Louis Maillard. So he was a Frenchman, a food scientist. And what he discovered is that when you put amino acids, or effectively proteins, together with sugars, you induce a reaction. And this reaction is called the Maillard reaction. And in contrast to caramelization, which involves just heating up sugars, the Maillard reaction involves proteins as well. So you have proteins and sugars and heat, typically above about 140 degrees, and then you get browning and flavor. So again, you get many byproducts, some brown molecules, some flavor compounds. The reaction is very complicated. I'm not going to go into the details, but it's just to show that effectively you need a sugar and a protein that react through this amino group here, and then the reaction continues, and you end up with a series of reactions where the molecules break up, they recombine, they react with other ones, they break up again, and you end up with a huge array of molecules. And here are some of the classes of compounds that you generate from this reaction. What I should point out is that maybe you recognize some molecules here. These ones we saw in caramelization. So you generate some of the same products of caramelization. But what is interesting is that most products that you generate from this reaction have nitrogen, N, and also have sulfur in them. So these atoms, you don't have them in sugars. Typically, you have them in the protein. So they come from the amino acid. So this N and the S come from the proteins. So that's why you need the protein. And they give this meaty, charred flavor that is really characteristic, for example, of a good steak. Okay? And yes, so this is the Maillard reaction. The Maillard reaction is everywhere. I mean, of course, it happens when you cook meat, but it also happens when you roast coffee, when you produce chocolate, when you bake bread, in champagne, or in black garlic. And in some cases, you don't necessarily have to apply heat for it to happen. So the Maillard reaction has several aspects that kind of affect it. So one is temperature. As I said, it's very important that you need high temperature. That's a very reason why we cook food at high temperature. Whenever there is a recipe that tells you to cook something at a high heat in oil, or to bake it at 180 degrees or so, it's really because you want to induce one of these reactions. So moisture, you don't want moisture because as long as you have moisture, you know water boils at 100 degrees. So as long as you have water, the temperature cannot go past 100 degrees. So the first thing you have to do is you have to evaporate off the water in order for the food to reach these higher temperatures that it needs for the Maillard reaction to start. The Maillard reaction, quite interestingly, happens faster at high pH. So, for example, when you add baking soda, and this is the reason behind pretzels. So that's extreme browning that comes from effectively the alkaline conditions. And it's what we call an exothermic reaction. So it releases heat as it happens. So that means that as it happens, it becomes faster and faster. And so you've probably experienced this when you're making toast, where it seems that it never ends, and you say, oh, it's never happening, then you look, and then suddenly it's all burned. And this is, I guess, you've been victim of the Maillard reaction. And so, so this is the second equation of the evening. It's about the speed of chemical reactions. So the students will recognize this is the Arrhenius law. It tells you how fast is the chemical reaction. So this is the reaction rate, depending on temperature. And so this depends on the activation barrier. So when you go from reactants to products, what you want to do is you want to cross a particular energy barrier. And so at higher temperatures, the molecules are much more agitated. They have more energy. So it's easier for them to cross the barrier. And so this is pretty much why most reactions happen faster at higher temperature. And so why am I saying this? It's because explains the reason why you want high temperature for the Maillard reaction. So unless you are applying high heat, the Maillard reaction is very slow. So the Maillard reaction happens at a reasonable speed, say within minutes or hours, at temperatures between 140 and 165 degrees. Also, this is the reason why you want to do that. However, as I said, sometimes you can induce the Maillard reaction at lower temperatures. For example, when you make champagne, or for example, when you make black garlic. And this is another of the recipes from Rebecca. And what you see here is that what you do is you have to heat the garlic at 60 degrees for 30 days. And so why is it? Well, it's simply because at 60 degrees, the Maillard reaction is way slower. So if you calculate using the Arrhenius law and you put in how much faster the reaction is at 150 degrees compared to 60 degrees, it happens to be 10,000 times faster. And this is because the way reactions depend on temperature is exponential. So a change of temperature makes an exponential difference on the rate of a reaction. And so if it takes 4 minutes to do a Maillard reaction at 150 degrees in a pan, if you multiply these 4 minutes by 10,000, you get 4,000 minutes, which is 1 month. So that's why you need to wait 1 month at 60 degrees to do black garlic. And this is all I want to say. I've spoken too much. And it's my pleasure to introduce Rebecca Clopath as our chef tonight. So she is an Alpine chef at the BIOF Tarach in Lohn, in Graubünden. And I've learned that Tarach means ground roots. So that's actually a really nice name. And the floor is yours.
Thank you so much. So now there is the difficult part for me, because thank you so much, Thomas. It was really interesting. I don't know how you are feeling, but for me it's always so nice to just have proper explanations for that, because I think it's very interesting as a chef, but also if you're cooking at home, to just realize what's actually going on all the time, like in every second. So, well, let's go one further. As Thomas said already, sorry.
So we have some samples actually for you. So the first set of samples is going to come out, but don't eat it.
Yes, not yet.
Just restrain yourself. There is going to be an exercise coming up.
Thank you. Just hold it in your hand. So while they're like bringing the cherry everywhere, I will explain a little bit what we are doing and why I'm allowed to be here. I'm invited. So thank you, Thomas, and to the ETH, and also to Remo and Sue, that this is possible. I think it's really nice. I was dreaming a long time about it, and I would definitely sit on the other side if I wouldn't be here. For me, it's also about inspiration. So everything actually starts with some thoughts which are growing in us, because I think humans are very curious. And I think we wouldn't stand here if we haven't been so curious. So we start to think, there are ideas growing. We do something out of that ideas. And when we water it, it's growing. And at the end, like just right now, what we heard, it's kind of giving us an idea and lightening up our mind what's actually going on in the section of chemics and physics. And yeah, so just to say, and that you know where we are in Lohn. It's a very small village on 1,600 meters in the Alpine area. And we are working, as you said already, with our Bierhof Tarach. And there we have like different points which are very important for us. So also to combine farming and cooking together. So yeah, for sure, we go with low temperatures, but we also go a lot with fire. And I think this makes it very interesting to cook with fire, to figure out the temperatures and what's going on. So for us, our values are actually, to be honest, and I think that sounds maybe a bit far, but I think, to be honest, like products are always honest, and the chemistry and the physics, you cannot cheat it. It is like it is. So we have to work with that, and from there we also get our inspiration for it. If you combine it with gastronomy in specific, I think it makes a lot to bring all this together. And for me, it's also very interesting to give it to other people. So that's why the cherries are going on. Yeah, very nice. Cool. But we also combine like not only what's going on right now, we also combine what's going on around us in our area and how we can put that on our plates. So, as I said before, we can cook like with low temperature. So this is for physical.
Yes.
And if you go higher, with the fire, for sure, you just start to do something different, no? And I think there it is going into the interesting part. So with the bread, we were lucky, a little bit too early maybe. I think for tonight, the idea was, as we have spoken the first time, so what are we going to do? Because it's a huge thing, and as Thomas said already, you have like, the world is open to you. I mean, you can cook everything, and you can reach so many different flavors. So we just bring to you the onions, which are like easily to combine, even when you don't cook often at home. And also the mushrooms, which we just put on one plate. You will help me to plate later? That's good. So I have someone who helps me. But also like the idea to have the Maillard reaction on your plate, or the caramelization. So you have this deep, earthy, or also like nutty, but this full flavor. And I think to combine it with something what is very light and fresh and easy makes it interesting for your mouth. And I think this is why I'm here to to maybe show how it can be interesting to put all this how you call it again when they had to clap?
Equations.
Equations, yeah. To make the equations to something what you have on the plate. So to realize what's going on, not only in theory, to put it in like an activity, what you do. And I think most of people like to eat. So I think it's a very nice combination. Yeah, this is just like to see a little bit what's going on, actually this plate, we bring it today also, the moss. It's always also very interesting. Nice. So for us, I think it's really important when we cook in our small place to be there with our mind. And I think it's also interesting to cook with our mind because there's so many possibilities going on when we do that, because we just start to understand what's actually going on, not only in the process, but also what's happening actually in our mouth and why. So it's kind of a connection, and with that connection, we bring nice creations on our plates. And the idea of tonight actually is to water all the seeds, especially that what you were telling before, that we can grow together and understand better what's actually going on all this process. Okay, good. It's the moment.
The moment of the cherries.
It's the moment of the cherries.
So everybody has gotten a sample? Yes?
There is a few.
Yeah, so can you pass it up there?
You feel ready, all of you? Okay, now there is something really interesting going on, at least for me. I always love that moment because the idea is to make an experiment, to be really aware for what's going on right now. And I think like all the process during cooking or having anything in your life, I mean, it is all over. If you are aware of it, it is much more intense. So the idea is to be quiet for the next 2 minutes and you make the experiment. And it's also really interesting to be in a room with so many people and no one is talking. Nice. I hope you had the time to enjoy also for your ears the silence. I think it's always so nice. I think it is a nice moment to maybe talk later about if you figured out something especially. And it's always also nice if you maybe have a neighbor to talk about it, because if you talk with other people about that experiment, not everyone will tell you the same. So also, like the reactions of what you eat in your brain with the hippocampus is like connected to something what you had already in your life, like experience, but also what you like and don't like. So I think it's going much further. And I would say, let's go to the next step. Thank you so much for listening to this round, and then let's go. Are you ready? Are you ready?
Let's cook. Well, I don't know. We're going to burn the place.
Yeah, we are ready here. We have
fire blankets, just in case. So we are fine. So, Rebecca, you tell me what to do.
Yeah, so I didn't know how much I were allowed to cook. Mm-hmm. So I bring everything. I have a top 10 list where I had like the most funny places to cook. The ETH is definitely very leveled on the front because I'm not even allowed to really cook. So I need to prepare everything, but that makes it easier for us, so we can talk a bit more. We will start to heat up the beurre blanc. And also there, I think you maybe can have a proper explanation for that, but I figured out that with about 65 degrees, the foam with this sauce stays the most stable. So that's what I figured out while doing it. So maybe you have a proper explanation for that.
Like maybe some people have remembered. 65 degrees sounds like a number we mentioned before, right? So this is typically the temperature at which proteins denaturate. And so that when they form this kind of like aggregated structure, they form like a nest, also a network, and that can stabilize a foam by trapping the air bubbles in it. And so that's a physical transformation in soft matter in action.
Soft matter in action. Actually, I would say being a chef is one of the most interesting jobs. There's so much going on all the time.
I think scientist is better.
Okay.
Actually, both is the...
Both. Let's go together. Great. So we have one plate. I also prepared like a porcini cream, which is like giving the fundament of the dish. So the idea is actually at the end to have saffron noodles with the porcini cream and to have beurre blanc, which makes it like you have a thicker cream underneath. And this is also about texture. I think it makes a lot also. And also there, I'm sure there is a proper explanation. And the idea is also to create different textures that people are like having a more interesting experience. Not that every thing has like the same point of texture. So here's the black garlic. We talked recently about it. I just grind it very thin. Are we still in the good? There is nothing going on.
Can get rid of the...
Yeah. So let's see. Are you good in mixing?
Mm-hmm.
Yeah?
Oh, no.
No?
Well, let's see. So what do I have to do?
So we nearly reach the point.
So what temperature is it?
62. And it's staying hot. So, okay, good.
Okay.
You teach me something. I was listening very properly. Now I'm doing
You
the same.
teach me.
Yes. So here you just mix it, and you need to hold the spoon like this.
Okay.
If you go too high, guys, be prepared. So always hold the spoon like, yeah. Perfect. And I will just go on with the noodles.
Perfect. So which one do I press?
The upper one.
Yeah.
Unless you want to go fast.
Yeah, no, I mean...
But it's as you say before, with like heat, sometimes fast is good and sometimes it's not that what we want.
Yes. Do I move it around or do I stay?
Yeah, it looks very good. Are you cooking at home sometimes?
Yes.
Good. And you think it's fine when we just when we go on with some heat later on? I'm very curious. He told me several times, but really don't cook.
Heat up.
Yeah,
yes.
Just only heating. Ooh, that can mean so many things. So I made a fond with some spices from local spices with Wiesenkümmel. Oh, wow.
Is it cumin?
Cumin, wild cumin, actually, yeah. And there's the saffron noodles. I boiled them before, that we don't have too much...
Yes.
And also that it's going faster. So I think we are good.
By the way,
nice.
the recipes, Rebecca has very kindly shared the recipes with us. So you will, at the exit, you will get one of the recipes as a takeout. And otherwise, you can find them on the Cook the Science website. So we will post them there. So you will be able to see all the ingredients.
Yeah. Mm-hmm. So no secrets anymore.
No secrets, no.
No.
So do I keep going with this?
No, I think you're good.
Okay.
You can just put it here, so it stays clean. Okay, now. I would say you can go with that.
Ah.
Then it was him, at least, no? So that's how I'm doing it, like first heating up the pan, then adding the oil, and then that what you want to have in it. But also there, I think there is many points of view to do it. But for me, like the oil is just getting destroyed with the time. Is that right? Like from the
well, I mean, there are like
perspective.
You cannot heat the oil past a point, and then there is this fume point exactly. I mean, you can use different oils to have a different a smoke point exactly. Thank you very much.
So, and why people are always thinking that olive oil is the only oil? Who is thinking that? Don't, I mean, if you have like a really good olive oil, it would be sad if you do it. We always use like a very soft oil, which is like not too flavory because the flavors will just be destroyed. Mushrooms. I don't go too crazy, okay? Yeah. And now I will not anymore talk about it. So you just can turn them. Sehr, sehr gut. Then I will start to plate here. I need to make sure that I'm not killing your table. It's so funny to do something the first time. Okay. Yeah, that looks really.
Yes, you can see the Maillard reaction here. Huh?
It's going on. Woo!
It's amazing. All of this brown. This is all flavor. Until it gets too brown, of course. Then it's a bit problematic. So, is it enough?
I think that's good. You can put the pan here. Yeah. This is our safe space. Cool. Then we just go with the noodles. And I think before we finish everything, let's take it out. Otherwise it gets too brown. No? I also really like that noise. So when I hear that, I know there is good flavor coming up. Yeah, this is German. You can go with another round.
Oh, should I continue?
Yeah.
So, get your umbrella.
Yeah.
So, what have you done here? So, you put the
noodles
on this paste.
Yeah.
Yes.
It's so there you have like the full flavor of mushrooms. Mm-hmm. Then we add the onion, which is also has been before like boiled a little bit, and then we grill it.
By the way, it smells amazing here. I don't know if you can.
Then we get the black garlic, which makes also like the idea is to catch up always something new.
So it's like it looks like pepper.
Yeah, because we don't use pepper in our kitchen, we need maybe to have something else. Yes. But it's much better than pepper. Very good. So some oil of the onions, of the green of the onion. Very good. You're hired.
Thank you. Well, you too. We can swap.
Yeah, that would be cool, no? So, in the very best case, you have a foam which stays quite long until it ends up to the guests. And here the interesting thing is for me also like if you eat the noodles, you have this creamy sauce, but also you end up with even more when you go down to the other mushrooms. So,
wow, the foam is great.
Yeah.
Yeah. By the way, be ready because Foam is a big topic in soft matter. So if you open any soft matter book, you'll find a chapter on foams. So that I would encourage everyone to do that after the lecture.
Nice. So also with the herbs, I think it's really important to have them to go up in a certain level of
So
freshness.
which herbs are these?
So, in English, guys.
So you
Maybe
take them from your garden, right?
Yeah, just very fresh. So there is a Vogelmiere.
Well,
knows
which you can
Vogelmiere?
buy at any supermarket, of course.
I have some rucola. I
Okay,
have
rocket. That's
Franzosenkraut. So there is a story behind. I think this makes it also interesting. Someone told me once that the Franzosenkraut is like something what no one wants in the garden, or definitely not on the fields where something should grow. So the French people put it into the German fields during Second World War that no carbs were growing anymore. But it's also nice to eat, but they didn't. It's true.
we trust you on that.
At the moment, there is no other chance, but I trust you also. Same. Cool. So, and also what, because we are talking about it, I bring some hazelnuts, which we roasted. And I think also there you have like this funny thing where you say it's like nutty. I mean, it's
Yes.
nuts, but still it's like even more.
Nuttier.
Nuttier.
Yes.
Hyper nutty.
Hyper nutty, yes.
Okay, good. I think we have everything. So this is one of the dishes which I would say is just like that.
So we clap also
The foam.
the phone.
Yeah, this is what I mean when I'm saying like what you are talking about is like the theory, and that's why we are here together to bring it on the plate and to make you remind on that day. I mean, you cannot try it now. If you want, you can try it. Or one person can come down and eat.
Oh, yes.
There is one portion.
Maybe we should ask Matt's questions, and then who gets the questions can. But maybe the umbrella guy.
Yeah, I think you were the
It's a
bravest
prize,
of
okay.
all. I have only a spoon. Are you ready to eat it with a spoon? I think you can handle it. You're very welcome.
Well, enjoy.
Enjoy. Woo-hoo. So let's put this to the sink so we have a bit more space for the next one.
Yes. Thank you.
How much time we still have?
Total about 15 minutes.
Okay, super.
Thank you. Yes, perfect.
So then, I brought something what was more like meant to be. So what I really like is to not having only dishes which are nice to eat. I think it's always important and more interesting if there is kind of an idea behind, as I say before, and also to have like a philosophy. And yeah, I really like to philosoph about food, but also about about your work. And that's why we bring something else to try for everyone. We bring stones, eatable stones.
I tried one before, and
Yeah.
it looks like a stone. She served it on a stone, so I wasn't sure which
Yeah, he
one
was
was
like-
the.
Really?
It was
I was like, you
amazing.
can eat it. I didn't told him what it was, so I will tell it now. It's actually just what you mentioned before. It's a caramel. So we made a caramel Teffeli. Probably a few people know what it is. And we add some minerals in there. So there is this. Shall I show it?
Yes, please.
It's it's like I make some advertisement now. So this is like they call it Gletschermineralien, and it's from the Gotthard Gletscher. And if you go to a drogerie and you say, well, I want to have some more iron or minerals in a natural way, they just give you this. And then you take one teaspoon every morning, put it in some warm water, and you drink it, and it's like beepty. You don't know if you like it or not, because it's very stony. Like maybe you remember yourself in something what you had in your childhood when you like tried to eat stones, or at least like lick them. I did that. It's not so fun.
So it's effectively like powdered stone.
It's powder of the Gotthard. So if you don't only want to try, no, it's true. And yeah, it's really funny, but I also think it's nice because like you are like in a way it's not to have the best. Is it good, by the way? Okay, cool. It's not to have here. The point is not to have the best flavor ever in your mouth. It's more about to start to think about what's actually going on around you, in our nature, in our habitat. And that's why we bring the stones. So we combine it with the scientific way from the caramel, and also like the philosophic way, because we want that you are going home tonight and talk about what was going on right now. No? I mean, I would like to. So maybe one day I can sit here and listen to you also.
Of course.
Everyone who wants can eat one.
Yes, for allergies there is a cream in it, so just in case. Genau. Otherwise it's just sugar.
So it's not vegan and there is cream in it, yeah. So you can, and I will go on with another funny story. And that's why I meant for us it's important to include everything. So if we go with the stones, we call it like the last bites in our menu. And we tell people like it's about über Stock und Stein. So you eat the stone, but before you reach stone, you are walking in a forest to go up to the mountain. That's why I bring some moss. And you can also eat it, actually. I put it in the small box to be humid.
Yes, I think it's faster.
So we made a biscuit with moss. Mm-hmm. And we add everything what we can find in our forest. So is it the fruit of the tree?
Should I keep some or give?
No, I think you.
But do you have enough for you? Oh, yes.
Yeah, if you need some more.
I know, I mean.
Yes, I need 2.
Yeah, exactly, I mean.
Give me a little bit of powder. Mm-hmm.
So we are adding a little bit of this magic powder.
It's really magic.
And so we're going to take a few from here. Well, actually, maybe we can...
Yes. I will maybe take a few more.
Yes, you can take more.
That's good.
Mm-hmm. Perfect. Perfect.
So if you are studying stuff from like early times, people were eating like also the fruit of the tree. Is it pine? Is it coin? What's the name again? Like from the larch, from the Swiss pine, and from the spruce. And I really like to study also like how people cooked earlier. And there were a lot of recipes actually to cook stuff like this. So if you want the stones, you don't need to wait, you can eat them.
Yes, and at the exit, you'll get the recipe for the stones.
Yeah.
And you see, I mean, before you saw it on on this here, this is how I got it served today. So you can see how I was a bit confused
Like,
about...
Rebecca, are you serious? Yeah. So we have some cream. Then we have some moss powder.
So how do you make the moss powder?
Just drying. So actually we just cut them off. We search for sure the ones which are longer.
So this is moss you find in the woods?
In the forest, yeah.
I mean, can you eat any moss?
You shouldn't eat all of them, but there is like, you can find the proper ones, but you will not die.
But then how
from
do you know
eating.
which one is the...
Because I know, I read it. I tried all.
Well, you have to tell us
here.
the secret at some point.
No, for sure, you cannot just go into the forest and harvest whatever you want. But there is always people asking me if it's okay to do it or not. And then mostly I ask if they, I mean, if you put aside that you live your life as you live your life, it's dangerous everywhere. But people are going so much into mushrooms and they are not sure if they pick the right ones. So it's much less dangerous to pick once the wrong moss, because there is really not so much going on. If you eat tons of it, yes, but as Paracelsus already say, die Menge macht das Gift.
And so what is this?
So this is now, you see it? Yeah, from the larch. I boiled it in water. And
so this is from the tree?
Yeah, this is from the tree.
Wow, I mean, you've taken the moss, the tree.
Yeah. I take what I have.
Yeah, no, it's amazing.
What's floating around. And yeah, I mean, all this is just like just next to us, very close, and we just do what you were talking before with it. So we create something what is probably unknown but still known. So that makes it interesting. So the idea is here to make a small walk through the forest, and when you eat it, it feels a bit like being in a forest where it was raining before, and then one or another moment you reach out of that rain and that forest, and then you come up to the mountains. Did you try the caramel? Is it okay? Is it funny to eat it? Because I also think it's really nice what your brain is telling you and what's actually happening. No? So let's see if I make it until here. No, not at all. Whoops. Okay, yeah. I think you need to try one.
Oh.
Would you like to?
Yes.
I mean, you eat the stone, you need also have to the forest walk.
Oh, nice. Wow, this looks
Maybe
amazing.
you can explain them what's going on. Maybe a Maillard reaction in your brain.
Oh, wow. It's so good. It's, yeah, I mean, sorry, I should learn how to do, like they do in television, you know, they say, oh, I can taste the moss, I can taste the...
No, you should say...
I can taste all the...
So,
they just list the components.
If you close your eyes, where are you? Still here? Probably.
Well, in the forest.
Sure.
It's really, I mean, it's hard to describe because it's a taste. I don't think I've ever tried anything.
More,
like
you know it from your nose, but not from the mouth.
No.
So this is making a next funny connection, I think.
Yes, it's very earthy and sweet, and it's really good. There is still one piece.
Cool. So I'm done. You?
Yes.
Do you have to say something else? Did
No,
we miss
I mean,
something?
no. Actually, maybe you can explain where you get the stone powder. Because I guess, like with the herbs, maybe it's not something you can find at every supermarket.
Yeah, for sure. I mean, you can go to the Micro Plus. No, they have the moss now. The stone powder is actually, You can find it in some drogerien. How to say it's not an apotheke, it's like a...
Yeah, so there are this...
Is it drugstore?
Drugstore, yes.
It sounds crazy.
Yeah, it's not drug.
Get the powder on the drugstore, okay. But you can also just get it online. I think that's much easier. Gletschermineralien, like the San Gotardo is in it. Do you need it here, probably?
Very good. Well, then let's clap for Rebecca. Thank you so much. That was really amazing, and I hope you enjoyed the connection between science and cooking, and you see how these concepts actually really apply to the stuff you do in the kitchen, and that you really see why is it that that a recipe tells you to do things the way you do. As I said, we have the recipes on the website, so you can download them and try to replicate the results. I mean, the most thing was really amazing, I have to say. And now, of course, this is the time to thank people. I think, it was a little bit of an experiment for me, because this is something I had in my mind for a couple of years now, and there has been a lot of work that has gone behind the scenes to actually prepare this, from the concept to getting people involved and so on and so forth. It's been a huge amount of work. And that, of course, is not only me. I really have to thank an amazing array of people without whom none of this would have been possible. And I have been really blessed to, in the course of this experience, meet amazing people that have really contributed so much to what we have here. So I'm going to start, no particular order, with Alicia Smith. Really, you have been a great partner since the start. And Sylvie from Life Science Zurich. Also really great perfect. Really great collaboration. Remo and Sue from Taste Lab that allowed us to get Rebecca on the stage, which was amazing. Roland from and all the communication teams at ETH. Andrea, and Anahita from the events management, the permit. So we got the permit to actually do this. So we have to thank them. Philip and all the camera team for an amazing job to film all of this and set it up so amazingly. I also have to thank my department, the Department of Biology, for supporting this. And also my institute, which is the Institute of Biochemistry. So check out the work we do. It's really amazing stuff. And also the Bringing Materials to Life consortiums, of which I am part of. And it brings together different research groups from ETH that are broadly interested in this topic of soft matter in biology, and in particular how soft matter underlies living materials. And of course, thank you all for coming. I hope you enjoyed and you learned something. As I said, at the exit, you will have the possibility to get a recipe card for the stones. And also there are feedback forms. We would greatly appreciate if you can take a few minutes to fill out a form and tell us what you think, how we can improve, because as I said, this was the first lecture, so we really want to know a little bit what went well, what went less well, and how we can improve to make the best events coming forward. So we have now 2 microphones that can go around. We have time for maybe a couple of questions to Rebecca also.
Well, while it's getting to the first space, maybe I'll take the first question, if you don't mind, which is, when you were whipping the cream, you had the spoon nearby. Yeah. Was this simply to prevent spillage, or is there something that really happens that's nicer with the foam when the spoon is nearby?
So I just figured out that you make much less mess. And also, like, if you mix it, I think the waves which are like going on because the spoon is just in the way, make more or gives much faster like air in it. So that's actually the reason. But I think everyone has his own technique. So this is just the one I choose for myself. Good, I don't have.
Can maybe stand up and speak?
Yeah.
So thanks a lot for the amazing seminar. That was really great. I have a question which is maybe a bit more technical. So we spoke about absolute temperature for the Maillard reaction and so on. How important is the difference of temperature between the food and the pan? So does it play a role? Is it something that, at least for charring, plays a role?
Yes, actually, yes. So actually, this is, it maybe becomes a little bit technical, but effectively you have different ways in which you can give heat. So you can give heat by contact. So would be like with the pan. Or you can give heat, for example, because you are in an oven. Okay, and so these are two different modes of giving heat, and they have different energies that are released depending on the temperature. Of course, if you put something in the oven, it takes much longer, effectively, to effectively transfer the heat as opposed to having it in contact with the pan. So the pan, of course, is very hot and it transfers the heat very fast because it's in direct contact. Whereas when you bake it in the oven, for example, it takes actually a longer time. This is, for example, a problem when you make pizza also, that you have the oven and, if the temperatures are not right, and in particular if the material of the oven is wrong, you can get the bottom of the pizza completely burned and the top is still raw. And so that's why people use stone, because stone has a different heat conductivity than, for example, metal also. And so that makes sure that you can reach higher temperatures and still not burn the bottom. So the material of the pan in that case would play a big role because that determines how effectively the heat is transferred from the pan to your food. Yes, it does. Yes, it plays a role, I would say, mostly in terms of the time you need to cook it. Because it takes, effectively, there is a formula that I didn't show, that would have been the third formula. Yeah, exactly. Yes, but it's effectively the logarithm, the time it takes to cook something is effectively the logarithm of the temperature difference, effectively between the outside and the initial temperature in the inside, and also the temperature that you want to reach. So it's a ratio of those temperature differences. So it takes longer if it's cold.
Thank you so much for this wonderful presentation. I'm terrible hungry now. I'm really curious, maybe you can say a little bit what happens to the nutrition when you heat it up a lot? Like, is there a difference also like the nutritional facts that's inside the food, or it doesn't change, or?
I guess maybe that's more something for Rebecca to know whether the food is better or not.
I think it really depends because there is like nutritions which you will lose for sure, but there is also some they will just connect better then. Let's say when you have carrots, you will for sure lose like, let's say, vitamin C. But if you boil it with oil, there the vitamin A is just opening, and as longer you cook it, as more it can cracks open, so you can have it like you can take it to you. So I think it makes a huge difference, but this is like a universe of information. And I think if you are really into that and you want to know what's exactly going on, I don't think it's the only way to say, well, we should eat everything raw because then you keep everything, because there is also many things you cannot take to you because your body is not able to release it then. So it just goes away without
Maybe
nothing
one thing also to say is that from a physicist's perspective, you could also play with pressure because these transitions that I showed, they happen at a particular temperature at the atmospheric pressure. But if you change pressure, you change the the temperatures at which these transitions happen. For example, the example is water. And so, for example, if you do that in a rotavapor also, which of course everyone has at home in their kitchen, you can actually boil water effectively at a much lower temperature. And so you induce the phase transition at a lower temperature, and that could, for example, allow to keep some of the nutrients. So maybe this is something we haven't covered today. We talk more about the temperature, but there is also other axes you could play, for example, with pressure, also to change the point at which the transition happens.
Yeah.
Oh, okay. Thank you for the talk. 2 questions, if that's okay. First of all, in the context of Maillard reactions, what's the purpose of oil? Because when you cook, you always put oil, and if you just put something directly on the pan, it just burns instead of having that nice reaction. And the second is, I have a person that I know that always puts claims on my cooking, says, "Oh, it's too brown, you get cancer from it." So maybe if you could tell me what I should say in response to that, back at that person.
Well, I guess just to reassure people, no one got cancer from being here today, right? With the
No.
no. So so I guess the whole point of using oil, as I said, is really in order to reach the higher temperatures that you need for the Maillard reaction to happen. Of course, there is a range of temperatures. Of course, if you increase the temperature even more, you make the reaction even faster, and so you risk to go beyond the point where you start to produce compounds that are not good. So that, of course, the dark, completely burned, piece of toast, as I showed before, that's, for example, an example where you've gone too far. And so the oil, it's a good way in which you can keep a particular range of temperatures that is in this range around 150 degrees or so. That is ideal for the Maillard reaction, of course, if you don't overcook it. And this is important because you cannot reach that with water. As I said, everything that has water will boil, and unless you remove all the water, you cannot go beyond the 100 degrees. So the whole point of the oil is to be able to kind of reach these higher temperatures. And then I would say, for these bad compounds, it's really about controlling the reaction such that it doesn't happen for too long or too fast. Yes.
Thank you for...
Yes?
Oh, sorry.
Yeah, sorry.
Can do that.
Oh, perfect.
Thank you for the amazing presentation and live demonstration. My question is, do you have any bonus equation for us?
Oh. Oh, wow. That's... So should I write an equation?
Maybe a little bit bright.
Okay, sure. Let's do that. So that's the equation for heat transfer. Excellent. That was great. I mean, not only people clap, and now they ask for equations. Good. I think
I have
we
one
have
last
maybe
question.
time for one last question.
Why should we wait 30 days for the garlic at 60 degrees when you said we can have it in 4 minutes at 150?
Yes, I mean, that's a question for Rebecca. I mean, why did you choose that temperature?
So, since I'm cooking, I figured out that for sure, in certain moments, we need to be fast. So we go fast with a high temperature. But we just discussed before about it. Let's say with the black garlic, there is possibilities to do it very fast. And also with high pressure, you can do it in let's say 6 hours, but the flavor is different. So if you give it a time, the flavor is different. And I think that makes a lot to figure out with which product you want to reach at the end the end product. So in which direction you want to go. And I think this makes it more interesting also. And a garlic which had time, I mean, we even do garlic longer. You can do it even 90 days. It's just getting darker. And it's just like nice to have these different flavors in your mouth. And I think in all the kitchens around the world, they work with exactly that. And I think time makes the different flavors and makes the diversity in the kitchen. So it's not, the easiest and the fastest way is definitely not the best way. So it really depends what you want to have at the end on your plate.
The next event, which is going to happen on the 12th of November, we will have another amazing person from the culinary scene, this time from Zurich. We have Jens Jung, the owner from the John Baker and the Jung Bakeries in Zurich. And we will explore the topic of elasticity, viscoelasticity, and the wonder of bread making. And thank you very much for coming. And let's thank again Rebecca.
Thank you.